just to remind you, your first take-home quiz is due this Friday. There's basically one question for each day of class we've had, so the first 3 questions you should be able to do now. After today, you should be able to do the 4th question, and tomorrow the 5th question. And then the following week is project 1 is due. Okay, so today we're going to talk about constructing antiderivatives analytically. That is, finding formulas for antiderivatives. Okay, so last class we constructed them graphically by sketching antiderivatives, numerically by using the area under the curve to come up with the values of the antiderivative function. But now we want to be able to come up with a formula for the antiderivative function. So I want to compute by hand the area under one arch of y equals sine x. So an integral that would represent this area would be the integral from blank to blank of sine x dx. Right, so draw a quick sketch of sine so I can know what my bounds should be. This goes to 2 pi, so this is pi. So if this is the one arch of the sine curve, I'm looking for the integral from 0 to pi. Okay, so we know that the fundamental theorem of calculus states that the integral from a to b of f prime of x dx equals f of b minus f of a. That is, the integral of a rate of change is equal to total change. So I am looking for a function whose derivative is sine of x. Okay, f prime is sine of x. What is f? An antiderivative of sine. Right. Yeah, so what's the derivative of cosine is negative sine, but I want my derivative to come out positive, so I'm going to use negative cosine as my function f. That's a function whose derivative is sine of x. So putting it all together, the integral from 0 to pi of f prime of x dx, where my f prime is sine of x, would be f of pi minus f of 0, and f is negative cosine x. So my integral from 0 to pi of sine x dx is going to be negative cosine of pi minus negative cosine of 0. What's the cosine of pi? Negative 1. So this is negative, negative 1 minus negative, what's the cosine of 0? 1. So I've got negative, negative 1 minus negative 1. Negative, that's 1 plus 1 is 2. Everybody got that? Make sense? Okay. What's another antiderivative for sine? This is sort of the easiest antiderivative. What would another one be? Plus something. Yeah, you can always throw on a constant and you'll still have another antiderivative because the derivative of the constant term is always going to be 0. So I could have another antiderivative, we'll call it f1. Could be negative cosine x plus 3. All right, so if I'm going to evaluate the integral using the fundamental theorem, I can actually use any antiderivative. The easiest one is the one where the constant is 0, but let's just quickly do it with the constant of 3 so you can see that it'll still work. Integral 0 to pi of sine x dx. So if I'm going to use cosine x plus 3 as my antiderivative, I'm going to have negative cosine of pi plus 3. That's what I get when I plug in my pi, and then subtract negative cosine 0 plus 3. So I plugged in pi, I plugged in 0, subtracting the 2. This is going to give me the cosine of pi is negative 1, so this is 1 plus 3. minus, the cosine of 0 is 1, so this is -1 minus 3, because I distribute the negative. Oh, I still have parentheses there, so I don't do that yet. Okay. Then distribute the negative. So I have 4 plus 1 minus 3, which is 2. Same thing we got when we used the constant of 0. So you can use any constant you want. Why not choose 0, right? It's the easiest one to deal with. All right, so let's try to find another one by hand. So if I want to do the integral from 1 to 3 of 8x cubed dx, I'm looking at this function here, and I have to think of a function whose derivative is 8x cubed. Yeah, it's got to definitely be an x to the 4th, right? So because to go backwards from a derivative to an antiderivative, when you take a derivative using the power rule, the exponent decreases by 1. So to go the other way, we should increase the exponent by 1. So it's definitely going to be x to the 4th. And then we have to figure out what coefficient to put here so that when I take the derivative, I get an 8. Right? So I need this to come out as 8x cubed. So when I bring this 4 down, what do I want to have as my coefficient? So when I multiply, I get an 8, a 2. 2x to the 4th. All right, so that is how we come up with the antiderivative of 8x cubed, and then I have to evaluate it from 1 to 3. So this is a notation that's shorthand for the fundamental theorem, as you put this vertical line after the antiderivative and put 1, 3. So that means 2x to the 4th. You read that evaluated from 1 to 3, and it just means plug in the 3, so you get 2 times 3 to the 4th, and then plug in the 1 and subtract them. 2 times 1 to the 4th. So 3 to the 4th, that's 81, I think. Yeah, and times 2 would be 162, minus 2 is 160. Okay, I'll leave the challenge for you to come back to later if we have time. So because finding antiderivatives is so closely tied to evaluating a definite integral, finding the area under the curve analytically, right, just writing it out on paper by hand, trying to find the area under a curve is really closely tied to being able to find an antiderivative, right? So that's what we did up here. We wanted to find the area under 8x cubed from 1 to 3. And the way you can do it by hand, using sort of like an algebra technique, an analytic technique, is to find an antiderivative. Because they're so closely tied together, we use the same symbol, the same integral symbol, to represent an antiderivative as we do to represent the area under the curve. Okay? We use integral notation to denote the antiderivative of f. So I just put this integral sign of, say, the function 2x plus 3 dx. And the antiderivative of 2x plus 3 would be x squared plus 3x plus c. It's the most general antiderivative. And so there's no bounds on the integral, that means find an antiderivative. When there are bounds, that means find the area under the curve. So we should notice no bounds. That means just find the antiderivative. So the process of finding an antiderivative is called integrating. So is the process of finding the area under a curve. We tend to call both of them integration. Even though they're really two separate processes, they're very closely tied together. All right, so here's the vocabulary associated with integral notation. The entire left-hand side of the equation is called an integral. So we've got an integral sign, we've got an integrand. dx, that tells you the integration variable, which will become more important when you take Calc 3. For now, because this is single variable, you're always just going to have x's here and a dx. Right? But when you take multivariable calculus, you might have x's, y's, and z's, and this dx is going to become important to tell you which is the variable you're thinking about. And then on the right-hand side, we have the antiderivative and the constant of integration. So you would read that out loud. The integral of 2x plus 3 dx is x squared plus 3x plus c. So like I said before, when the integral sign doesn't have any limits of integration, then the integral is called an indefinite integral, and it means find the antiderivative. Okay. The dx is a necessary part of every integral. It's because you don't use it in the analytic process of finding the answer, it's easy to forget to write it, but the notation is meaningful. It always goes at the far right. For indefinite integrals, the plus c is mandatory. Omitting the plus c will cost you points on a quiz or a test. All right, so find these two integrals. Take a minute. The indefinite integral and the definite integral. Okay, so for the first one, the indefinite integral, the integral of 3x squared dx, there's no bounds. So this is just shorthand for saying, please find an antiderivative for 3x squared. So instead of having to write out a sentence to tell you what I want you to do, it's quick symbol. So what is a function whose derivative is 3x squared? X cubed. So this, I would say, this equals x cubed plus c. Right? You need the plus c to get the general antiderivative. All right, and then when I want to do the integral from 1 to 2 of 3x squared dx, that means find the area under the curve from 1 to 2. So this should be a number, right? When you're looking at a definite integral, that means area under the curve. The answer should be a number. And it's closely tied to the antiderivative, right? So if we did this one first, this one should be easier. So the definite integral, take the antiderivative, you get x cubed. You can use any plus c you want, so let's just use 0 because it's the easiest. So this is going to be x cubed evaluated from 1 to 2. So that vertical line means evaluated from 1 to 2, and that means plug in the 2, plug in the 1, and subtract them. So this is going to be 2 cubed minus 1 cubed, which is 8 minus 1 is 7. And we should check on our calculator, at least when you're doing things at home where you're allowed to have a graphing calculator, you might as well check. So 3x squared and I want the integral from 1 to 2. Well, looks like I need to go a little bit higher. I gotta go higher than that. Go to 15. All right, so now I want the area from 1 to 2, so I do second calc, integral 1, 2, and it'll shade my area, and it tells me that that area is 7. Okay, so finding antiderivatives is really important for us for this class. So, yes. Mm-hmm. Instead of using your calculator. Oh, okay. So you look at the integrand. Look at the integrand. So this guy, I'm taking the integral of 3x squared. So that's the curve I want to find the area under. The way you find that area is you could use your calculator, right? Or you can take an antiderivative and plug in the top bound and the bottom bound. Does that make sense? Okay. All right, so finding antiderivatives is an important goal of this class, being able to find an antiderivative. And just like in Calc 1, finding derivatives was an important goal. We had a lot of shortcuts for finding those. We're going to develop shortcuts and techniques for finding integrals or antiderivatives. So we're going to look at some basic ones first. And and then as the semester goes along, we're going to develop more and more sophisticated ways of finding antiderivatives. So first, how do we reverse the power rule? Right? If I want to find a function whose derivative is x to the n, what should I do? Or maybe I can just do it in 2 steps here. Well, what's the exponent going to be? N plus 1. It's definitely going to be x to the n plus 1. Y over n plus 1. Oh, okay. It is over n plus 1. Can somebody explain why I have to also divide by the n plus 1? Yeah. Yeah. So when I take the derivative of this fraction I just wrote down, I'm going to take the exponent n plus 1 and bring it down in front, where it will cancel with the n plus 1 that I put down underneath. And my exponent will be reduced by 1, leaving me with just an x to the n. Make sense? No, it's over the n plus 1. Let's do an example. Let's say x to the 9th. I want the integral of x to the 9th dx. Okay. So I definitely am going to have to do an x to the 10th to get an antiderivative. So I'm trying to come up with a function whose derivative is x to the 9th. If I just take the derivative of x to the 10th, when the 10 comes down, I'm going to have a coefficient here of 10. And my exponent will be 9, right? So I'll have an x to the 9th, but I'm going to have this 10 in front that I don't want. So if I divide by 10, then the 10s will cancel. So if I take d dx of x to the 10 over 10, bring the 10 down, I'm going to have 10x to the 9th over 10, cancel x to the 9th. Okay, so this is like your n plus 1, because your n was 9. Make sense? All right, how about the integral of 1 over x dx? A function whose derivative is 1 over x. ln of x. Oh, sorry. And this actually has to be absolute value of x, and we'll talk about why another time. How about the integral of e to the x dx? E to the x. A function whose derivative is e to the x is e to the x. A to the x. A function whose derivative is a to the x. Yeah? It's definitely going to have an a to the x in it. Where do I put the ln of a? Denominator. Yeah. Denominator. Because the derivative of a to the x is a to the x ln a. Right? So if I have a to the x and I take its derivative, I get a to the x ln a. But what I really want to do is have a function that when I take its derivative, I just get an a to the x, no ln a, right? So what I need to have in here is definitely an a to the x, because that part is good, right? And if I divide by the ln of a, then that would be a constant that just comes along when I take the derivative. So it would be like 1 over ln a times a to the x ln a, and my ln a's cancel. So my derivative, my function whose derivative is a to the x is a to the x over ln a. How about a function whose derivative is cosine x? Sine x. A function whose derivative is sine of x? Negative cosine x. Because the derivative of cosine is negative sine. So if we want the derivative to come out positive, we throw a negative in front. If you want to take the derivative of a sum or difference, sorry, the antiderivative or the integral, you can take the integrals separately, just like you can with derivatives. So this would be the integral of f of x dx plus or minus the integral of g of x dx. So that's handy that you can integrate term by term, just like you can differentiate. And also, similar to derivatives, you can take a constant and pull it out in front. So the integral of c times f of x dx is c times the integral of f of x dx. All right, let's try to use our new formulas. So this is an integral of a difference, and I've got some constants. So the first thing I want to do is make my life easier by separating the integrals into separate terms and pulling the constants out in front. So this would be 2/5 times the integral of e to the x dx minus 3/4 times the integral of x to the e dx. And then the integrals look much simpler, right? I've just got this one and this one. All right, what's the integral of e to the x dx? E to the x plus c, yeah. So this is going to be 2/5 times e to the x plus c. All right, what's the antiderivative or the integral of x to the e? X to the e minus 1 over e minus 1. This is a power rule because e is just a number, so it's x to a power. So I use the power rule. So this is going to be x to the e minus 1 over, yes, plus 1. Thank you. Plus 1. And then you can distribute if you want. Oh, and I forgot my plus c on this one. Call this C1 because it might be different than that C. Could be different. Doesn't have to be the same. We'll just leave that like that. Okay. How about the integral of x minus 1 over root x dx? Ideas. What do you want to do? Yes, good. So always a good idea when you're doing an integral that looks a little complicated to simplify the integrand first. And one thing that we can easily do is change the square root to an x to the 1/2. All right. What else can we do to simplify the integrand? Sure, I can do that. So this would be x to the negative 1/2 times x minus 1. Sure, it does. What can you do now? What do your instincts scream at you to do when you see a set of parentheses? Distribute. Distribute that x to the negative 1/2. So this is going to be an integral. X to the negative 1/2 times x to the first is x to the 1/2. X to the negative 1/2 times negative 1 is negative x to the negative 1/2 dx. Now I can use the power rule on both of those terms. So my antiderivative power rule says I should increase the exponent by 1 and divide by that number. So 1/2 plus 1 is 3/2. So I should have x to the 3/2 and divide by 3/2, right? Or multiply by 2/3. And then x to the negative 1/2, what do you get when you add 1 to negative 1/2? 1/2. So I'm going to have x to the 1/2. And then I should divide by 1/2, divide by that exponent, or multiply by its reciprocal too. It takes several problems over a few days to be able to switch your mind to antiderivative rules, right? And then it takes even a few more days to be able to go back and forth and do whichever one you want and not get confused about which rules you're using. So just be patient with yourself. It will become more familiar. Keep in mind, there are many integrals we can't do yet. Like, if I wanted to find the integral of x sine x dx, that's a simple enough function. It's just a product of x and sine x. But I can't think of a function off the top of my head that has that as its derivative. It'd be a lot of guess and check. So any of these three we can't do yet, even though they're relatively simple functions, but we will come up with techniques for how to do them. Hi, can I help you? I don't know. What class are you looking for? Okay, I'm gonna skip over the challenges for now. And here's some practice for you. Working with antiderivatives. So for each integral, find an antiderivative of the integrand, then use the antiderivative with the fundamental theorem of calculus to evaluate the integral, the definite integral, and then check numerically using a calculator. And if you finish this, you can go back and look at the challenge problems. Okay, so I need an antiderivative for x squared. A function whose derivative is x squared would be what? X cubed over 3. Okay, so my definite integral is going to be my antiderivative, x cubed over 3, and then evaluated from negative 3 to 3. All right, so when you do the plugging in part, plug in from negative 3 to 3, you always plug in the top number first. So I want to plug in a 3. So it's handy to be like, okay, that means I'm subtracting plug in 3 from plug in negative 3. So I have these two parentheses set up ahead of time, because also when you have a really long antiderivative, sometimes you just forget to plug in the bottom number because you just spent 10 minutes plugging in the top number and it feels done. So I always do this first. Set up your two parentheses. I got to subtract two things. The first thing I got to do is plug in my 3. So I get 3 cubed over 3. And then plug in my negative 3. Negative 3 cubed over 3. Then simplify each set of parentheses and then subtract. So that's 27 over 3 is 9 minus negative 3 cubed is negative 27 over 3 is negative 9. So that's 18. Okay, so these are just small habits that I've developed over doing these for a long time, and they can be handy. You can use them or not, but they help me from making mistakes. And then another thing I do a lot, when you have a really complicated integral, if your antiderivative is very complicated, which it wouldn't be on a test because I'm going to give you non-calculator tests, but if you're doing your homework and your antiderivative is really complicated, like pretend x cubed over 3 is really complicated. Okay, so I go to y equals and I type in my antiderivative, x cubed over 3. Then I would say, okay, I have to evaluate my antiderivative from -3 to 3. Plug in a 3, subtract, plug in -3. So I use my vars key. y1 at 3 minus y1 evaluated at -3. Right, so you can have your calculator do all the arithmetic. All you have to do is find the antiderivative and type it in y1. And you get 18. All right, so let's look at the next one, x minus 2. What's a function whose derivative is x minus 2? Yeah, x squared over 2 minus 2x is my antiderivative, and I'm going to evaluate that from -1 to 5. So that means I have to plug in a 5, and I have to plug in a -1, and I have to subtract the 2. So I'm going to set up a parentheses for plugging in my 5, and set up a parentheses for plugging in my -1. When I plug in my 5, I get 25 over 2 minus 10. And when I plug in my -1, I get 1/2 minus -2. So then simplify each parentheses and subtract. So 12.5 minus 10 is 2.5. And 1/2 plus 2 is 2.5. So you get 0. And again, we could do a similar thing with the calculator. Just type your antiderivative into y1. X squared over 2. Oops. Squared over 2 minus 2x. And then y1 evaluated at 5 minus y1 evaluated at -1. So this is a good thing to check to see, is my mistake in my antiderivative or in my arithmetic, right? Because if you get the right answer this way, then your antiderivative is right and you messed up your arithmetic. So it's a good way to figure out which one you messed up if you didn't get the right answer. All right, how about 2 to the x, a function whose derivative is 2 to the x? Two to the x over ln2. And then I'm going to evaluate that from 0 to 3. So set up two parentheses, one for plugging in 3, one for plugging in 0. So 2 cubed, that's 8. And 2 to the 0 is 1. So then those have the same denominator, so I can subtract the numerators and I get 7 over ln2. And this is the kind of question that your calculator cannot help you with getting an exact answer. right? 7 over ln 2 is an exact value. It's an irrational number. Your calculator can only give you a decimal, right? So in general, in math class, we like exact answers. So we can still check our work, though. So I have 2 to the x divided by ln 2. And then I got to plug in a 3 and plug in a 0. And I get a decimal, 10.09. I can and then type this in and see if it's the same decimal. Same thing. Okay. So we can be confident that our answer is right, but this calculator cannot give us the exact answer, right? And when I do the area under the curve thing, it also will only give me a decimal. All right, let's look at number 4, integral from 0 to pi of sine of t plus cosine of t. So I got to come up with a function whose derivative is sine of t plus cosine t. So what function has as its derivative sine t? Negative cosine. And what function has as its derivative cosine? Sine. Okay, so there's my antiderivative. Evaluate that from 0 to pi. So I got to plug in a pi, and I got to plug in a 0, and subtract. So when I plug in pi, I have negative cosine pi plus sine pi, and then plug in 0, I get negative cosine 0 plus sine 0. The cosine of pi is negative 1. So this is negative 1, which is 1. What's the sine of pi? 0. And the cosine of 0 is 1. So this is negative 1 plus the sine of 0 is 0. This is 1 minus negative 1, which is 2. All right. A couple of people finished these 2 already, but other people were still working. So I'm going to give you a few minutes to think about these. And if you're done, there's a challenge problem on the next page. You can go back to the challenge problems from earlier.